talk about the Performance-Based Standards project, which I think a lot of you know about. We also call it the Smart Truck project, and it's a little bit more advanced in terms of engineering, mechanical engineering, vehicle dynamics than the RTMS. I think it's important to understand the PBS approach to vehicle design. It's not just about putting longer and heavier vehicles on the road. There's a lot of science that goes behind it. And I'll just tell you a little bit about the pilot project in South Africa, the monitoring results, just to give you an update of where we are now. I showed this slide earlier, and I said that the RTMS had specifically significant benefits in terms of vehicle maintenance and drivers. The PBS approach to vehicles is focusing on the design, and you'll see now what I mean. It's not about designing a chassis or a bin. It's about certain key parameters on a vehicle that can help to improve its performance on the road. This is a project that started way back in the 70s in the United States, where the University of Michigan did some research on trying to find out the cause of truck rollovers in the United States. At that time it was about 10,000 a year. And the University of Michigan did some fundamental research on vehicle dynamics. However, it was Canada and New Zealand that took that and started what we call a performance-based standards approach to vehicle design. And then it was followed by Australia, who did a lot of work on that. Australia now has over 9,500 PBS vehicles in the country, and I'm not talking about road trains now. That's sort of a separate category. So South Africa was the 4th country in the world to look at PBS for vehicle operations. And the aim of the pilot project was to see whether that technology could be used in a country like South Africa, which is quite different in terms of our drivers on the road compared to countries like Australia and New Zealand. And the purpose of the pilot is to see how these vehicles can reduce road wear per ton kilometre, how they can reduce vehicle trips, improve safety performance, improve transport productivity, and reduce emissions. So I've got a few little video clips to show how a vehicle's performance on the road is significantly less safe than a motor car in terms of speed, going around corners. This is a clip from the US, a truck going down a hill. Just press something, there we go. This is another one where the truck's not going really very fast, but due to the height of the center of gravity and various other things, it's a lot less stable on the road than a car. This I got from Dan Terrell in Durban last year. Truck going a bit fast, admittedly. And this is down Wingfield Interchange in Cape Town. So, besides the importance of drivers and vehicle maintenance and correct loading, the prescriptive approach, which is on the left-hand side of the slide, has got some fundamental flaws in it. So the prescriptive approach is what governments use to have developed regulations to regulate vehicles on the road, including trucks. And they basically look at what the vehicle looks like in terms of dimensions and mass. However, they've got the prescriptive approach has got certain weaknesses or disadvantages. It constrains productivity and it constrains innovation. The performance-based approach governs on-road performance, and I'll explain that in the next few slides. So you look at how the vehicle behaves on the road rather than what it looks like. It does allow heavier and or longer vehicles on certain parts of the network that are approved by the road authority. So in our road network in South Africa, in any country, you've got high standard roads and then you go right down to residential streets. So trucks, you can actually allow longer trucks on certain roads like highways, but those trucks should not be allowed to go on the lower order roads. So that is a sort of optimizing your road network in terms of productivity, and it does promote innovation. So we decided for the pilot project in South Africa to adopt the Australian performance standards, which had already been included in their regulation. That was, I think, in 2008. And as I mentioned earlier, one of the guys from the National Heavy Vehicle Regulator based in Brisbane was out here for 10 days, and we ran 2 smart truck courses, and he gave a lot of updates on the PBS project in Australia. And essentially what PBS is about is to define certain maneuvers, and these are not cast in concrete, but this is what sort of come out from the PBS initiatives in those countries I mentioned. There's a low-speed turn at 90 degrees, a low-speed 90-degree turn at 5 kilometers an hour, a high-speed lane change maneuver, a rollover maneuver, high-speed pulse steer, etc. Then there's some drivability standards. Now those maneuvers, which are simulated on computer using quite sophisticated software, are used to measure performance standards, which is on the right-hand side. And I'll show you some examples. So from a low-speed turn, you can measure low-speed swept path, you can measure tail swing, front swing, etc. And the PBS vehicle that one wants to operate must pass all of these performance standards. It must pass the low-speed performance standards, it must pass the high-speed performance standards, and also the drivability standards. The drivability standards are to ensure that that vehicle can maintain acceptable speeds when it's traveling on the road with its payload. So here's an example from Australia of low-speed swept path or off-tracking. And this is a standard, legal, prescriptive truck tractor semi-trailer, and you can see there's a little bit of off-tracking. The second truck is also a prescriptive vehicle in Australia, 19 meters, 2 trailers, and you can see its increased length results in higher off-tracking. But the following vehicle is a PBS vehicle. It's 1 meter longer, so it's 20 meters long, but it's been designed for a maximum swept path. So although it's longer, you can see its off-tracking is less than the previous vehicle. This is a prescriptive vehicle in Australia, legally allowed to 25 meters, but it's got a very poor off-tracking. So it cuts considerably into that opposite lane. And then the last vehicle is a 26 meter PBS vehicle, A double, and you can see it may have steerable axles, I'm not sure, but it's got a very good off-tracking. So the point is that the way the prescriptive approach to try and limit off-tracking is to limit the length of the vehicle or the wheelbase. But that doesn't necessarily mean that vehicle has got a good performance in terms of off-tracking. So that maximum swept path that you see there, maximum width of swept path, that's a performance standard. So irrespective of the length of the vehicle, you can design a vehicle to have a maximum swept path. Now that's just one of the performance standards. And that hopefully illustrates the difference between a prescriptive approach and a performance approach. This one is a high-speed transient off-tracking. It's a high-speed lane change maneuver, and the performance standard is related to how much the rearmost trailer moves from side to side when it does that lane change maneuver. Now this slide shows on the left-hand side the baseline vehicle. This was the first PBS vehicle in timber. So the one on the left is a legal 22-meter rig, 56 tons. It's a rigid truck with a drawbar trailer. And the one on the right is the first PBS vehicle that we ran or introduced into South Africa. It's 27 meters long, and it's got a combination mass of 67.5 tons. and this baseline vehicle failed this performance standard. The response of the trailer was unacceptably high. That's how much the trailer moves from side to side. Whereas this one is a PBS vehicle, and you can see how it performs when it does this lane change maneuver. Because of certain parameters, in this case it's primarily the position of the hitch. So the hitch position on the baseline vehicle is quite far back, whereas on the PBS vehicle it's got what we call an underslung hitch. It's moved as close as possible to the drive axle unit, and that has a big impact on the dynamic performance of the drawbar trailer. The third test I want to show is the rollover. So here you accelerate a vehicle on a constant radius curve, and you measure the acceleration, the lateral acceleration, at the point that the trailer or the truck rolls over. So the blue one is the baseline vehicle, and the red is the PBS vehicle. So the simulation just shows gradual, the vehicle is speeding up, you get increased lateral acceleration, and you get rollover. So the minimum requirement for this performance standard is 0.35 G. That red vehicle now rolls over at about 0.36 G, whereas the baseline vehicle, which is a legal vehicle in South Africa, it rolled over at 0.27 G, which is considerably lower than the minimum requirement. So it just means that that baseline vehicle has got a much higher chance of rolling over if the driver's going a little bit fast around at an interchange. There are also infrastructure performance standards to ensure that the vehicles are more road friendly than the baseline vehicles, and also to ensure that bridges are not compromised. I'm not going to spend much time on this, but this graph shows the blue diamonds are roadway characteristics of baseline vehicles, and you can see that some of them have got quite a high roadway characteristic. In other words, they cause quite a lot of road damage per ton of payload, whereas the red squares are all PBS vehicles. All these vehicles here are in mining. Mining baseline vehicles and mining PBS vehicles. And using this approach, we can ensure that all the PBS vehicles are consistently road friendly. I'm not going to go into more detail there. So the question for the committee that we formed was, can we operate PBS vehicles in Africa? Some people said, oh, we've already got PBS vehicles, high capacity vehicles, but not very safe. I don't know if this is just to illustrate that not all technology is appropriate. Oh, maybe this, I'm not sure if this is going to play.
Emma.
Okay, so we just have to be sure with the pilot project that these sort of quite high technology vehicles can interact with the traffic that we have on our roads. So we started a pilot project. This slide is a little bit out of date. We're over 300 vehicles now, and in fact, about almost 190 million kilometers have been traveled since 2007. Started off with 2 vehicles, and it's gradually increased. The main products that are being moved are fuel, timber, mining. We've got coal separate, processed sugar, there's beer, there's now Coca-Cola, aluminium, etc., paper reels. And you can see from the map that most of the PBS vehicles are operating on the east side of the country, KwaZulu-Natal, Mpumalanga, and Limpopo. We still have some challenges with the Western Cape and Northwest Province. The Northern Cape has started to approve a number of PBS vehicles now. So generally speaking, there's good cooperation. I say generally speaking, but except for those 2 provinces. I think one of the difficulties with roads authorities is to understand that just because a vehicle is longer and or heavier doesn't mean it's worse. In fact, it's better. And this is what's being found in the other countries that are implementing PBS. We did a strategy in 2007. We obtained approval from the Minister of Transport at the time. We've also developed a rules document which explains to an operator who's interested in how to participate, what the process is. We've developed some tools like a route assessment tool that can help for a particular interchange, whether a PBS vehicle can safely negotiate their turn. This was a 30-meter vehicle at an interchange. And then an assessment on the left is at an intersection in Durban. Look, you set the boundary lines and then see if the vehicle can safely go through. And then the one on the right is at a depot. This was the SA Breweries study. And then at the moment, we require this type of reporting back from the operators on a monthly basis from their telematic system to show the routes that each PBS vehicle has been using. The one on the left is a forestry operation, and the one on the right, a platinum operation. Now I just want to show you a couple of examples. The relationship between the PBS project and RTMS is that the operator must be RTMS certified in order to participate in the project. We've had a little bit of resistance in that respect, but if you look at the non-compliance of trucks on our roads, as I showed earlier today, the authorities would not, most of the authorities that I know would not consider PBS vehicles if there wasn't that assurance through the RTMS that there's good compliance in terms of all the things we've spoken about this morning: speeding, drivers, overloading, etc., vehicle maintenance. So we started the project in Timber. You can see some of the vehicles that started off there. This was the first one. I showed you the simulation, the 27-meter vehicle with Timber 24. This is operating in Mpumalanga, one of the ones in Mpumalanga. This one is not over length, it's 22 meters long, but it's got a 67-ton combination mass. This is a longer timber vehicle. This one has got steer axles at the two rear axles of the Trident, and those steer axles greatly improve the turning performance of the vehicle. The low-speed swept path that I showed you earlier makes a huge difference. There's a Bolo World mining side tipper. Adrian is going to talk about the Bolo World PBS projects in a minute. But this vehicle is also not over length. It's operating up in Limpopo carrying platinum ore. Two Tridents. This vehicle does in the order of 40% less road wear. It's got a 50-ton payload, and it's a very safe vehicle on the road. And I think Adrian said these payloads are sometimes worth around 20 million. So you can know these vehicles get looked after very carefully. And there's one of the road trains down in KwaZulu-Natal that Unitrain's operating. The top one and I just want to illustrate another performance standard. The top one is the baseline vehicle, which is not a PBS combination, but they had been operating for about 10 years. And the bottom one is 42 meters long. It's 185-ton combination mass, but it complies. So one of the performance standards is Rearward Amplification, and the baseline vehicle in this case failed horribly. Sorry, I'm not used to this little pad. So you put a pulse steer in at the steer axle, and then you measure the response of the combination. And in this case, you can see it's not a very, very good combination, whereas the PBS vehicle obviously is to be designed so that it passes the performance standard. It's quite an aggressive maneuver, but you can see the combination is quite stable. Sugar bottom dumper in KZN. There's quite a number of these cold side tippers now operating mainly in Mpumalanga. Also a 50-ton payload, and a much bigger challenge to get this vehicle to comply, because with the same payload, the center of gravity height of this vehicle with the coal is much higher than, say, with platinum or chrome. So the center of gravity height of the payload is a critical parameter to performance of the vehicle, the high-speed performance. So you have to, the profile of the bin had to be changed and modified until you could get the center of gravity down enough so that this combination passed all the standards. Then there's a fuel quad that's being operated on various routes around the country. I think there are about, how many are you guys operating? 13. So there's probably about 35 of these operating around the country, if I had to guess. It's got a steer axle right at the back, and it's got a lift axle. That front axle of the quad is a lift axle. We did an estimate on the sort of 500 kilometer lead distance, sort of Durban, Johannesburg, and taking into account the lower fuel consumption, less return trips, less roadway, less accident rates, and estimates and all that, you're actually saving about 2 million rand per 1,000 tons of payload moved on that 500k trip. Then there's a Beefmaster B triple for cattle. This is the SA Breweries 11 axle, what we call an A double, and this one is also a lot more road friendly. Being 30 meters long, the route approvals are a little bit more challenging than obviously a 23 or 24 meter rig. So it's mainly constrained to the highways, and this is for primary distribution, obviously not secondary distribution. There, when they started operating 5 of those vehicles in the Eastern Cape in 2016, after 3.5 months, they had saved 100,000 kilometers compared with their baseline vehicles. So they did the same amount of work with 100,000 less kilometers, and they saved about just over 26,000 liters of fuel, or 12.5% savings. And then Yapi showed you this one. We've got the car carriers. A lot of work has been done with the car carriers. We had VDS sharing their RTMS case study. The big challenge with car carriers is a tail swing. So again, that slow speed maneuver, you can see the tail swing is the amount that the rear corner of the trailer swings out when the vehicle does that 90-degree turn. Now, car carriers have got a very large rear overhang, most of them, because of the nature of the payload. And a colleague of mine did a bit of a study looking at typical car carriers in Australia and South Africa. With our prescriptive regulation, we allow rear overhangs of up to 7 meters. That's possible in South Africa under the Road Traffic Act. Whereas in Australia, there's a cap of 3.7 meters. So it's determined as a percentage of the wheelbase, but in Australia there's an absolute maximum, whereas in South Africa we don't have that. So in Australia, the maximum tail swing is about 300 millimeters, whereas in South Africa, our car carriers, the old generation car carriers, had tail swings up to 1.25 meters. And all the new car carriers now have to be PBS compliant if they want to operate under permit with the extra height and length. And I know from feedback that I've had from VDS that big reduction in accident or crash rate, part of it is as a result of this much reduced tail swing. So in summary, some of the benefits, this is just going back to June last year. On average, we're saving 86,000 trips a year, or 22% reduction in trips, about 14 million kilometers less per year, and 2.2 million liters of diesel less. Greenhouse gas reduction, 12%. On average, a reduction in roadway of 13%. And the crash rate currently is sitting at a 50% reduction. So the measurement up until end of August, with about 190 million kilometers, the crash rate of the PBS vehicles is 50% less than the baseline vehicles. In Australia, that figure is sitting at 46%. As I said, they've got over 9,500 PBS vehicles, and with their project to date, they've saved 1.5 billion kilometers with their PBS fleet. I mentioned that a lot of the baseline vehicles are not safe. We did a study of all the baseline assessments that have been done up to date. On the left are the PBS vehicles, level 1. Haven't gone into the different levels, but of all the baseline vehicles that we've assessed, 56% of them fail one or more of the performance standards. So more than half of the baseline vehicles in this project that have been assessed do not comply with the PBS rules. And if we look at them, 73% fail 1, 18% fail 2 of the standards, and 9% fail 3 of the standards. The most common standards that they do not comply with is the rollover, which I showed you, the rearward amplification I also showed you, and then yaw damping coefficient. So those are the common, and those are all high-speed performance standards. So in summary, we're running this pilot project. We're hoping to bring it to conclusion fairly soon. When I say fairly soon, in the next year or two. Things move slowly with these projects. But to demonstrate, and to date we have demonstrated significant gains in all these areas with this approach to heavy vehicle operations. The European Union have developed a framework using the PBS approach, and 2 of my colleagues were involved in that project through Cambridge University, and their big drive is to reduce emissions. So the whole Falcon project in Europe, which involves a PBS approach to heavy vehicle operations, is about how can they reduce emissions from road freight transport. In our case, I think the big benefit is reduced crashes, but also reduced transport costs and reduced emissions. Thanks very much.